which was describing the different sources for body water input and body water output. So how do we get water into the body and how do we lose water? So this sort of slide, this sort of flow chart is describing the different inputs and then the different areas of communication between our different body compartments. So we know that we ingest most of our water, not only through physical liquids, but also through food. A lot of the food we eat has water as well. So think about vegetables, fruits, they have some bit of stored water. That comes into the GI tract or the digestive tract, and then some of that water is reabsorbed across and ends up in our interstitial fluid compartment and our plasma, right? It moves into the blood vessels and into our interstitial fluid area, which forms our extracellular fluid compartment. And then some of that water, a very small amount, is eventually excreted in feces. So not a lot of water is excreted here, but some is, although this is mostly solid waste. And then we do have the secretion of some water in order to facilitate the movement of that waste through the tract. Now, from our plasma and interstitial fluid, we then have communication between other fluid compartments. So we know we have communication between our cells, right? Our cells are communicating across the cellular membrane and into the plasma as well. We also have communication between our connective tissue. So bones and ligaments and tendons, they can regulate or communicate water in between our plasma and those tissues as well. And then we have communication into the kidneys. So this is really where we're focusing our attention. These three processes of renal exchange, where we filter most of that water into the tubules of the kidneys, we secrete further some amount of substances and water, and then we can reabsorb some of that back into our plasma, back into our interstitial fluid area. Okay, so this is the real important area where water is regulated. Most of our water regulation happens at this level, between secretion, absorption, filtration from the blood to the kidneys and vice versa. We also have some areas of minimal water loss, so things like sweating, bleeding, respiration, our salivary secretions, our mucus production. Those other minimal areas are also contributing to some form of loss as well. And then obviously most of the loss is going to happen through the excretion of urine, right? Most of the liquid, the loss of fluid is happening via urine excretion. Okay, so this is just showing us how water input communicated into the plasma, which is like the central area. These are our blood vessels. And then we have water output, which is contributing to this water balance that happens in the body. Now, as we talk about balance, a system is in balance when the solutes in water that enter are the same amount of solutes in water that exit, and they're doing so at the same rate. And so we have no overall change in the total water in the system or in that substance or in that in this container we can think about for this example, because the inputs are exactly equal to the outputs. And this is in a state of balance. And this is where the body likes to be in terms of urine production. And again, we can think about this in terms of caloric production as well. We can talk about a positive state of balance or a state of positive balance. And this is where the solute or water that is entering the plasma does so at a faster rate than what is exiting the plasma. And so we end up building up the amount of water in that system or in that container. And so the quantity will eventually increase here because we're not outputting as much as we're inputting, or we could think about it as we're inputting excess, and so the output doesn't match the input. And then a state of negative balance is going to be the opposite. So the quantity decreases in this system or this container because the quantity of output is significantly greater than the quantity of input. Okay, and to sort of plug some examples here, we can talk about this as being a state of excess water. So think about if you're holding on to water, diabetes is one way to look about this, or hypertension is another way, right? I remember I said if we have high solute concentration. We have lots of salt in the plasma. We end up storing water because that solute is not leaving, so the water doesn't leave. And we can think about this state of negative balance being just dehydration. So if you're dehydrated, if you're not bringing in enough water, if you're sweating excessively, if you're hemorrhaging, you end up in this negative state or this state of negative balance. Okay, and then obviously this first container is going to be the ideal place that the body likes to be in, which represents homeostasis. All right, now when we speak about solute and water balance, there are two important cells that are in the distal part of the tubules that help to regulate water balance. These are the principal cells and then the intercalated cells. So the principal cells are really involved in water movement, so the movement of water from the tubules back into the blood or vice versa. So remember, thinking about that barrier for reabsorption or secretion, water moving across that barrier is regulated by the principal cells. And then the regulation of solutes as well. So electrolyte, sodium, potassium, chloride is also regulated through these principal cells. And then the intercalated cells more are involved with acid-base balance. So basically the secretion of hydrogen ions is really where the intercalated cells come in. So this regulation that happens in the distal tubules and in the collecting ducts, this is why we say that this area is regulated, because these cells are controlling the flow of these substances, water, solutes, hydrogen ions, from the tubule over into the peritubular capillaries or the plasma, whereas in the proximal part of the tubule, in the proximal convoluted tubule, there aren't really any cells that are controlling this. This is happening freely and unregulated. Okay. All right, so now we move to objective 3. Let's see if there are any questions. Okay, no. So now we move to objective 3, and this is to explain the control of water balance and osmolarity by antidiuretic hormone. Now we've talked a lot about antidiuretic hormones, so this should be a review at this point, right? We talked about it as it relates to blood volume regulation, right? It's involvement in the kidneys and that long-term regulation of blood volume. We talked about it as it relates to the endocrine system. Remember, ADH is one of those hormones that is secreted from the posterior pituitary, right? If you remember that hypothalamus pituitary axis, it's one of those hormones that is released from the hypothalamus, stored in the posterior pituitary and released, and it has its effect on the kidneys. Now, as we speak about water balance, these are the topics that we'll kind of touch on. We'll talk about osmolarity. We'll review water reabsorption in the proximal tubule, because we talked about this in our previous unit. So this will be really a review. We'll talk about the water movement along the loop of Henle, and this is where we'll look at the establishment of the medullary osmotic gradient. And then we'll look at how this gradient facilitates water reabsorption in the distal parts of the tubule and in the collecting duct. All right, so going back to this water balance and this flow chart that we talked about. So the intake or the inputs of water in the body are from the GI tract, so whatever you bring in from the diet, and then from metabolism as well. And if you think about cellular metabolism, now this is going to be way back to ANP1, where we talked about the process of cellular respiration and oxygen acting as that final electron acceptor. So when we make ATP via that process, we also make water. So a small amount of water is produced as a byproduct of cellular respiration. So that is another input or intake of water as well. So whatever we ingest, about 2.2 liters per day, whatever we create as a byproduct of cellular respiration, about 0.3 liters per day, is what generates our water inputs. This is totaling about 2.5 liters per day. And then we can speak about water output. So there are insensible loss, there is sweating, there is also from the GI tract that's excreted, and then what's excreted from the kidneys as urine. So we excrete about 0.1 liters per day as a part of solid waste. right? So a very small amount, very minimal. And this can be influenced by things like diarrhea. So diarrhea can increase how much water we excrete, but typically it's not a whole lot that is excreted through feces. Another water loss is what we call insensible loss. So things like I mentioned earlier, mucus production, the water that is used to humidify air, so a part of the respiratory tract, things like salivary secretion, sweating, all of that is also amounting to about 0.9 liters, which contributes to other losses. And then the bulk of that is going to be about 1.5 liters per day, which we know is our urine secretion or excretion that happens through the kidneys, okay? Now, if we add all of that up, that is also totaling about 2.5 liters per day. So what we can see here is that our total water input for a normal healthy system, right, a normal healthy adult, which is at homeostasis, the water inputs are exactly equal to the water outputs, okay? And this is why it's so important to be ingesting enough water, because we're going to be losing water through other processes that we sometimes can't control, like sweating, right? Like urine, like feces, to get rid of waste. And so we need to be ingesting enough water to match that output. Otherwise, we're going to fall into a state of imbalance or throwing off homeostasis, okay? Right. Now, talking about being in a state of imbalance, this brings us to speak about different water balance states. So we can be normovolemic, or we can describe normovolemia as having a normal blood volume, meaning that your water inputs match your water outputs. We can also describe hypervolemia as having a higher blood volume due to a positive water balance. And this means that your water inputs exceed your water outputs. And then we can also describe hypovolemia, which is having a lower blood volume due to negative water balance. And this is going to be a state where your water outputs exceed your water input. So this will be more like dehydration, hemorrhaging, excess sweating, and things like that, right? This hypovolemia where water outputs exceed your water inputs.